In this lecture, we're going to talk about precipitation. We're using that solubility product to predict when something will precipitate or if it will. So let's think about that. Going through or relating it to what we know about equilibrium, that we can calculate a KSP or a K value or a KA or a KB and know the concentrations that we would expect of our reactants and products at equilibrium. But we can also take a situation where we don't know if a system is at equilibrium, calculate the Q value in the exact same way, and compare it to the equilibrium constant value. And in this way, we can tell if a system is at equilibrium, if we don't know, or if it needs to form more products to reach equilibrium, or if it needs to form more reactants to reach equilibrium. And we've used this before when we talked about chemical reactions, and now we're just going to apply it to solubility and precipitation. So we've got a beautiful picture of silver nitrate and sodium chromate forming silver chromate, which is that red solution on the picture. And it's showing a precipitate forming as we pour the aqueous solution of one into the aqueous solution of the other, of our two reactants. And because when we combine these concentrations, the value that we get when we calculate Q is larger than the equilibrium constant, it means that we're actually going to see a solid form. Remember, when we talked about solubility product, that KSP value is going to be right before a precipitate would form. So it's really telling us the amount, the molar solubility that can exist before we have a solid. So thinking about that, if you calculate Q in the same way that you would calculate KSP, so in our case with solubility, Q is going to be equal to the concentration of the ions. If we're looking at this silver chromate, we're looking at the silver chromate as a solid in equilibrium with silver ions, two of them, and a chromate ion. So our Q value that we would calculate would be our silver ion concentration squared times our chromate ion concentration. The same way we'd calculate the solubility product. Now, when we calculate that value, if it is equal to our solubility product, or KSP that we would look up in a published table, then we know the solution is saturated. There is no solid forming. But if we increase those concentrations just a little bit, we'll shift that equilibrium. Oops, that just moved my screen. We'll shift that equilibrium to the right, or sorry, the left, and form product. And that's, or sorry, reactant, that would be a solid. I flipped a couple words there. My apologies. Now, if we calculate Q and Q is actually smaller than our solubility product, it means the solution is unsaturated. An unsaturated solution is a solution that can still have more of those ions present before a solid would form. So it can still dissolve more silver chromate in this case. Now, the case when we see a precipitate is when a solution Q value that we calculate is larger than KSP, or solubility product. In this situation, we have more ions in solution than can be supported at equilibrium. And so that if we have more of these products, it means that equilibrium shifts and we form more solid. That solid then will look like a precipitate that just crashes out of solution, like we're seeing in this image right here. So for solutions, if you want to know if something will precipitate, you want to calculate Q in the same way you would calculate solubility product, compare it to the known solubility product, and if it's larger, then you know you'll have a precipitate form. There is the case where you would have a supersaturated solution where that Q will be larger than the KSP, and it still wouldn't come out. An example off the top of my head of this is simple syrup. Now, we can take advantage of different compounds having different solubilities and use it to selectively precipitate one compound over another. And we can use this to separate mixtures of compounds. And being able to separate things in chemistry is a whole subset of the field, because once you make something, you need to be able to isolate it. So this is an example of a solution that contains a lot of things: magnesium ions, nickel ions, copper ions, and mercury ions. It's a lot. And we can actually separate these into two different solutions or precipitates. Um, and we do it by having different conditions with which we have the precipitate form. So if we add dihydrogen sulfide under acidic conditions, we'll have copper sulfate and mercury sulfate that will have a much lower molar solubility than manganese sulfate or nickel sulfate, or sulfide, sorry. And so these will precipitate out of solution while our manganese and nickel ions stay in solution because they haven't reached that point with which they'll start forming a solid. Their Q is smaller than their solubility product. So once we have those precipitate, if then we bring the pH of the remaining solution up to something that's basic, like a pH 8, we'll see that that solubility of manganese sulfide and nickel sulfide ends up becoming much smaller. And then we'll see those two compounds fall out of solution as a solid. And so in this case, we're looking at controlling that solubility with pH, but we can also control it by adding a certain amount of a reagent that forms one of our ions to precipitate out that has a lower solubility, separate that solid from the rest of the liquid, and then continue to add the ion to precipitate out the next ion as well, the next cation as well. And this is going to be the foundation of our first lab, which is about qualitative analysis of ions, where you're trying to separate out a group of ions that are all in one solution and determine which ones they are. So let's start with some example problems. I'm going to do these actually in a following video. So give them a try first if you have a second. The first example is going to be just calculating when a precipitate will form, if it will, when we have a combination of concentrations of two different products, or sorry, two different reactants. Then we're going to do a example problem where we have two solutions mixed together and they will not form a precipitate, but then we're going to add in something like chloride that'll cause them both to precipitate at different concentrations of chloride ion. And we could use this to separate the two. And we'll look at what concentrations each of those are at with this problem. So give that one a try as well. And then watch the solutions in the following videos.